Here's a boundary between two materials. Let's say the first material is air with an index of refraction of 1.00, and the second material is, let's say, glass with an index of refraction of 1.50. It varies a little bit, but we'll say 1.50. We're going to make this my normal line. This is the line that's always 90 degrees to the boundary, and we're going to shine a beam of light. It doesn't really matter what color. We'll assume the index of refraction is the same for each of the colors. It's not quite, but it's close enough for purposes of what we're doing right now. First beam of light we're shining here at a really small angle as measured from the normal line. When it goes from air to glass, low index of refraction to high index of refraction, the light is going to slow down. We're going from small to big N. We're going from big to small V. So it's going to slow down, and because it slows down, the angle is also going to decrease. So it's going to look something like this. Now, if I increase the angle of incidence pretty dramatically, theta 1 is a lot bigger than it was before, but theta 2 will still be smaller than theta 1 because the light slows down when we go from low to high index of refraction. Increase the angle of incidence even more to a really high angle of incidence right now. Theta 1 is much bigger than it was before. Theta 2 is a lot bigger than it was before, but theta 2 is still smaller than theta 1. Theta 2 goes down because V goes down, and V goes down because N has gone up. Let's draw another picture now, though. This time, let's put glass on the top. Once again, glass has the index of refraction of 1.50, and air has the index of refraction of 1.00. This time, let's shine a ray of light at a small angle as measured from the normal line. This time, because we're going from high to low, big to small n, n goes down, speed goes up. As speed goes up, theta goes up. This time, theta 1 up here is smaller than theta 2. Let's increase the angle of incidence a little bit more. Angle of incidence is higher, theta 1 is bigger, theta 2 is also going to be bigger. Because as you go from high to low index, you're going from low to high speed. Let's increase the angle a little bit more. What happens now? Well, the ray of light actually skips right along the boundary between the air and the glass. This is a point at which a phenomenon called total internal reflection begins to occur. Total internal reflection is a phenomenon whereby light doesn't refract when it hits a boundary between two materials. Rather, it reflects. And this is the point where it begins to occur. We'll call that the critical angle, theta c. Anything below that angle, refraction happens. Anything above that angle, not very well drawn, but anything above that angle, reflection happens. Total internal reflection. It's kind of like skipping rocks, right, in the water. You throw a rock straight down almost, and it goes into the water. It changes speed and it changes direction, but it still goes into the water. Throw it down at a little bit of a bigger angle, it changes speed, it changes direction, but it still goes into the water. But if you throw it at a really, really big angle like this, as measured from the normal line, what happens to the rock? It skips right off the boundary, right? Now, the one problem with that analogy is that when light does that, it has to be going from high to low index of refraction. In other words, water to air. Whereas rocks can do it from air to water, because rock's not a wave, right? We're not really talking about total internal reflection when we're skipping rocks, but it's kind of like that. It kind of reminds us of that. So total internal reflection is a phenomenon whereby instead of light refracting, light will reflect off of a boundary when theta 1 is greater than a certain angle that we're going to call theta c. It only happens when you're going from high to low index of refractions. Never happens. Never happens going from low to high. It's physically impossible to get total internal reflection when you're going from low to high index of refraction. What is that critical angle? It's the minimum angle, the minimum theta 1, the minimum angle of incidence at which total internal reflection will occur. Anything above that angle, reflection occurs. Anything below that angle, refraction occurs. The page here. I'm going to give you a couple real life places where total internal reflection occurs and some of the implications of that. We got a pond here, pond filled with water, and there's a guy standing pretty much at the edge of the pond. He's either a really small guy or that plant is really big, but it doesn't matter. He's standing by the edge of the pond, and let's assume that light or whatever can make it through that plant. We got a fish in this pond. Fish is down here. He's smiling. He's all by himself down there, enjoying the solitude of in the refreshing cold water on a sunny, hot day. Light from the sun is going everywhere, including into this pond. And when it goes into this pond, it refracts, it bends. But that's not what I want to look at right now. I want to look at after the light reflects off of the fish. There's millions of rays of light reflecting off of the fish. There's one ray that I want to look at in particular. That's this one. If this ray of light reflects off of the fish, goes up in this direction, encounters the boundary between the water and the air. Remember, the index refraction of water is about 1.33. For air, it's about 1.00. As it's going from high to low index of refraction, from big to small n, it's going from small to big V. V increases. Theta increases, and the angle theta 2 ends up being bigger than the angle theta 1. So we say it bends away from the normal line. Theta 2 is bigger than theta 1. Goes right into my eyes. I happen to see this fish. Now, where do I see this fish? Kind of tricked a little bit, right? Because I think that light's always traveled in a straight line, which means that my eyes and my brain interpret that beam of light as having come from this spot right here, even though it came from here. So where do I see the fish? I see the fish, but I see it not as deep, and I see it further back. The real position of the fish is closer, yet deeper than what I perceive the position of the fish to be. That's not total internal reflection, right? Light's still refracting when it's going from the water to the air. But watch what happens if I step back. Maybe Mama showed up and said, "You're too close to the pond. You're going to fall in and drown." So you back up. And when you back up, that ray of light that was reflecting off of the fish's head still reflects off of the fish's head, still refracts, but it sails right over your head. You can't see it anymore. It's there. If you're taller, you can see it. But right now, I'm not taller, so I can't see it. But remember, there's other rays of light that are reflecting off of that fish. Let's pick another one. Let's pick this ray of light that's reflecting off of the fish. That ray of light encounters the boundary between the water and the air at a bigger angle. You can see that theta 1 right here is bigger than theta 1 right here. Because we're going from water to air or high to low index refraction, and that's a pretty big theta 1, we may actually exceed the critical angle right now. If that angle, that blue one, is bigger than the critical angle, then that ray of light that we want to refract over here and go into my eyes, it may actually reflect instead. What do I see now as I'm standing back there, a certain distance away from the pond? I see the top of the pond. You ever notice that? You're looking in water you see things at the bottom, right? You see the rocks at the bottom, or if it's on a golf course, you see the golf ball that you're looking for on the bottom or whatever. But then when you step back, you don't see the rocks anymore. You don't even see the bottom of the pond. That's because the light that would go into your eyes in order to see it is reflecting off of the boundary between the water and the air. Total internal reflection. It doesn't mean that somebody else can't see it, but the light that you need to see isn't coming out. Where would you need to be in order to see this fish from this blue light, that is, this blue ray? If I wanted to see this fish with this blue ray, this one particular ray here, I'd need to be underwater. I'd need to be laying right there. Where would I perceive the fish to be? Now, it's not as odd as it seems. Although I would perceive the fish to be way up there, I would also perceive the water to be way up there as well, right? So it wouldn't look like the fish is floating around in the air. The fish would still be floating around in water, except it would all be above you instead of below you. Make sense? It's like a mirror, right? You look in a mirror and you think that things are on the other side. Got another one for you. The last one for the day, and then we'll pack it up. What do you see there? It's a diamond, yeah. It's a cross-section of a diamond. All diamonds are supposed to be cut at very precise angles. When you go buy a diamond, guys, when you're going to buy a diamond for your the person who you want to marry in about 15 years, they're going to probably tell you about 4 different C's, 4 important characteristics of diamonds when you buy them. Girls, by the way, when somebody does ask you to marry them, make sure that you think about those 4 C's as well and think, is this guy cheap or is this guy just not very smart? When he gives you a diamond here, or something that's not a good quality diamond. Here's the 4 C's that affect the quality of a diamond in no particular order. Color. Usually we want no color. Sometimes diamonds have color. And if they have a deep color, like a really bright or deep color, then they can be very, very valuable because they're very rare. But generally, you want no color. You don't want to have any color on your diamond. Like you don't want some pukey yellow thing, right? Second one is clarity. You don't want it to be foggy. You want it to be clear. Okay, and you don't have to be an expert to know that there's no color and the diamond is clear. The third one is carats, the size of the diamond. You don't have to be an expert to tell that this is a big diamond or this is a small diamond. But the fourth one, as important as any of the rest of them, but not very well understood, is the cut. You can't just take a diamond and cut it any way you want. As a cross section, the diamond has to look like this. Now, it doesn't matter what the shape of it is looking from above, but as a cross section, it has to look like this. Here's why. Diamond has a high index of refraction. It's about 2.42 as compared to air, which has an index of refraction of 1.00, and glass, which has an index of refraction of about 1.50. When you're looking at this diamond from the side, most of the light that enters this diamond is going to come in from above. Now, when it comes from the air to the diamond right here, it's going to slow down dramatically. It slows down by a factor of 2.42. So it's like a third, basically, of the speed that it's moving through the air. But it doesn't change direction because for the most part, that light is coming straight in. But when it gets to this boundary right here, between the air and the diamond, it has to do something. If this angle is smaller than the critical angle, the light goes out here. If it's bigger than the critical angle, it's going to reflect. Diamond has a really high index of refraction, much higher than glass. Because it has a high index of refraction, it has a low critical angle versus glass, which has a high critical angle. Because diamond has a lower critical angle than glass does, it means it's easier for the light to exceed that critical angle. It's easier for the light to reflect. So you get more light reflecting from the inside of a diamond than you do from the inside of glass. Reflects off of that side, comes back over here, hits this side, and well, that's bigger than the critical angle, then so is this, and it reflects back up here. every time you see a reflection taking place, it sparkles. So if you get 1,000,000 rays of light coming in and bouncing off of two surfaces each, then you get 2,000,000 reflections or 2,000,000 sparkles. If you're using glass as opposed to diamond, coming in, striking at the same angle, but remember the index of refraction for glass is lower, the critical angle is higher, it's harder to exceed the critical angle, you're more likely to get this out of the glass than you are the reflection. So it reflects less off of glass, less sparkles off of glass. But why is the cut important? Why is the angle important? Well, let's say you're driving on the highway from Calgary to Okotoks. You know when you get to just out of the city there and you see that guy parked on the side of the road selling golf balls and fish? Ever buy fish from that guy? Maybe it's good, but I've never bought fish from a guy that also sells golf balls. But let's say that he happens to be selling diamonds as well. Okay, and you're thinking, one of you guys is thinking like, I think it's about time I propose to my girlfriend. I think I'm going to stop and buy a diamond from the guy that sells golf balls and fish. And you buy a diamond, and you're like, boy, that's a huge diamond. It's really pointy. Looks more like a carrot, except it's not orange. Maybe it is. The light comes in straight like this. Look at this. We've way exceeded the critical angle here, like way bigger than the critical angle. That's definitely going to reflect. Okay, that's better than the other shape was, right? But watch how it reflects. It goes down here. And then look at this. Oops, we're not bigger than the critical angle, so it's going to come out here. We get one reflection, one sparkle, but remember when it was this shape, we got two reflections or two sparkles. Make sense? What if it's not long and pointy like this one? What if he sells you a diamond that looks like this? Kind of short and stubby or fat. Light goes in like this. Uh-oh. We're not bigger than the critical angle now. So what happens? It doesn't even reflect once. When you have this shape, doesn't mean it's the only shape where light will reflect, but it maximizes the amount of reflection that can take place and therefore maximizes the sparkle. So girls, if somebody gives you a diamond ring and it doesn't sparkle, okay, it's either cut wrong or it's like cubic zirconium or something like that. In either case, you should probably turf them.